Hi, welcome to Mathematics with Tom. I am Tom, and today we're going to talk about finding the angle between two vectors. So let's begin with that. So this is actually a continuation of use of the dot product. So let's call it that. Let's call our title today is the dot product continued. Dot product continued. And let me refresh us. Let's say we have two vectors. We'll just make a short one. Like let U and V be vectors in R2 so that we need all the details. So that let's say that the vector U has components U1, U2, and V, the vector V, is components V1 and V2. So then let's see the dot product. Then U dotted with V is equal to U, so let's write that out. That's the vector U1 and U2 dotted with the vector V1, V2. And then the dot product says that what we do is it's a sum of the products of component-wise. So it's U1 times V1 plus U2 times V2, and then we stop. But if there was more components, it'd be plus, and we'd continue down to U3 times V3 and continue through all the components of the vectors. And so we can write this as U1 V1 plus U2 V2. That's the dot product. So today we're going to find out what is the angle. How do we use the dot product to determine the angle between two vectors? And we're going to look at the vectors U and V. So I'm going to draw a picture here. This is in R2. So let's look at it about like that. Not like that. And there's my x-axis, and here's my y-axis. And I'm going to draw these vectors so that they're not too canned looking. This will be my vector U. And we'll also have a vector V. Let's make V a short one that's a little steeper, and U is a longer one. So there's the vector V, and here is my vector U. So we want to find the angle between these vectors. We're going to call that angle here theta. But we don't know what theta is. So we're going to use some right triangle trig here. Let's look at this. Let's grab another color like this pretty pink. And here's salmon. I like the salmon. Let's use the salmon color. So if I look at the salmon color, this is theta. Theta is this angle here between U and V. And then let's call this angle between U and the x-axis, this angle here. We'll call this the angle alpha. And then in our purple chalk, this angle, the angle from V off of the x-axis, we'll call that the angle beta. So let's start with the vector U, and then we'll be able to understand the vector V, and then we can put this together. So notice this. U has components of U1 and U2. So that tells me that this is the point u1. And if I come back this way, this is the point u2. Now, well, vector u is about alpha, so let's see what we can write here. Well, what we can write is this. We know this. We know that, so let's do this. We can write, or we know, how about that? We know that if I take the cosine of alpha is equal to the adjacent side, that's u1, divided by the hypotenuse. Well, the hypotenuse, it's not the vector u, it's the length of u. So this is over the length of u. And then, so what can we write? Let's do this. Remember this problem, we need to solve for u1, because what we want to do is we need to better describe our vector u and our vector v. So we can write this as u1 is equal to, we multiply both sides by the length of u, so it's equal to the length of the vector u times the cosine of alpha. Okay, so that's this length right here. I'll just write it in here. It's the length of u times the cosine of alpha. Now, let's do this again. We need to find this vertical side over here. Well, how do we do that? Well, we know the angle alpha, and we also know that the sine of alpha is the opposite side over the hypotenuse. Let's write that. So we know this, and what else do we know? We know this, and that the sine of alpha is equal to, the opposite side, that's u2, divided by the length of u. I'm going to write it this way, or we can write this as u2 is equal to the length of u times the sine of alpha. There we go. Now we actually know something very specific, and we have it in terms of angles here. So let's rewrite our vector u. Rewriting our vector u. So u is equal to the length of u. I'm just using my u1 component, u1. So it's the length of u times cosine of alpha, and it's the length of u sine of alpha. Okay. At this point, what I'd like you to do is take a moment and go through the exact same process and rewrite the vector v in terms of v1 using v and v2 using sine and cosine, but this time you're going to do it in reference to the angle beta. So I'm going to step aside, pause the video, and then we can write that later, or we'll come back. Okay, I'm back, and hopefully you're ready. If not, again, please pause. Make sure you finish this. Let's see. You should have come up with then that the vector v is equal to the length of v times the cosine of beta, and it's v2 is the length of v times the cosine of beta.
Sine.
Oh, sine, thank you. Yes, this is the sine. Let's fix that. Sine beta. Okay. So let's keep something in mind. So far we have alpha, we have beta, but the whole question was theta. So what I want to do is make a few notes. So let's come over here and let's record that. Note. we want theta. That's what we're after. But look at what theta is. Theta is equal to, if you take the angle beta and you subtract the angle alpha, you'll have beta. So let's see what we can do with that. So it's beta minus alpha. Okay. At this point, we know nothing else other than the dot product about vectors. So let's take the dot product of u and v and see what happens. So here we go. You're going to take the dot product of u and v. So this is the length of u, cosine of alpha, length of u, sine alpha, dotted with v. Well, v is the length of v, cosine theta, and the length of v, sine v. Okay, the dot product, we're going to use what we did at the very beginning today. So that means we take the first component of u times the first component of v. So that's going to be the length of u times the length of v times the cosine of alpha times the cosine of beta, plus, then we have the u2 component, so that's the length of u, I'm going to just times the length of v, cosine alpha, sine beta. Sine alpha, sine beta. Let's notice that the cosines and sines, there's nothing clean about that. Let's factor out the length of u and v. So let's write this as the length of u, length of v, times cosine alpha, cosine beta, plus sine alpha, sine beta. Now, it may not look like we've done much here, but we've done almost everything. The one key that's not easy to remember, I don't think it is, but there's a trig identity for this that cleans this up. This is the same as the length of u times the length of v times, this whole expression is the cosine of a difference of angles. The cosine of beta minus alpha. But that's what we wanted. It's right here. And there's our answer. This is equal to the length of u times the length of the vector v times the cosine beta. Now, let's put this together. I'm going to solve for cosine of theta. So let's do that. Solve for cosine theta. And if we do that, what we get is this. We get the cosine of theta is equal to u dotted with v divided by the length of u times the length of v. Now, at this point, we need to stop and provide some clarity. Notice this. U and v, each one of these, those are both real numbers. So both of these are just real numbers, and a real number times a real number is still a real number. But u is a vector. V is a vector. But the dot product, when you take the dot product of two vectors, well, that result is also just a number. So look at what happens. You're taking vectors, the dot product, and you get a number divided by a number. But let's take this one step further. Let's take u divided by the length of u. And we're going to dot that with v divided by the length of v. Now at this point you may wonder, well, can you do that? And the answer is yes. You can, if you remember that u, the length of u, it's a scalar. It might be easier to think of it as the length of u as some scalar. Like we've used the letter C and the letter D. This can be like a C. Times the vector u. This whole piece is now being dotted with the scalar 1 over the length of v times the vector v. And what I want to show you is what this piece, whether you look at it as u divided by the length of u, or you look at it as 1 over the length of u times the vector u, what I want to show you is what these are. So we need an example. So I have an example for you. Let's come back. Would it be better to go left?
I can keep going now.
Okay. So let's try this. Let's do this. Let the vector x be, 1, 2, no, don't write that. No. 1 square root of 3. There's something more interesting. And the vector y, let's write this as, how about 1, 0. Okay, so let's graph that. I'll wait till you're ready.
I'm ready.
Okay, all right, so we have, let's graph x and y. Let's graph something like this. Oops, let's make our vertical axis vertical. Make the horizontal axis horizontal. And so I have something like maybe 1, 2, and probably about 2. And 1. Okay, so this is my x, this is my y. And so if I first, let's graph these vectors. Let's do this in orange here. So my vector y, that's this one right here. That's the vector y. And then the vector x is over 1 up root 3. Root 3, about 1.7, so it's probably about there. That's the square root 3. So I have my vector x right there. Okay. Now, let's find the angle between them, theta. We're going to just start with, actually, let's do something else. Notice that if this side is 1, and this side is the square root of 3, we know already what that is. This is going to be a 30, 60, 90 right triangle. And if you double the short side, you should get the long side. Well, let's just double check. Let's find the magnitude of x. Is it really just twice that? In other words, is it 2? Well, let's try it. So the length of x is the square root of 1 squared plus the square root of 3 squared. Well, that's 1 plus 3, that's 4. Its square root is 2. Sure enough. We already know the answers to this problem, but there's even more yet to see. So 2 is the length of x. Okay, it gets better. Let's see if in fact that theta is 60 degrees. Well, let's try this. So we already found that. I'm going to use our formula. Let's just put it in right here. Cosine of theta is u dot v over the length of u times the length of v. Let's do this in pieces. First, let's take u dotted with v. So that is 1 square root of 3. Dot that with 1, 0. That's 1 times 1 plus root 3 times 0. And that's just 1. And let's see, we already found the length of, this should be x and y, sorry. Let's fix that. Okay, and we already found the length of x. That was 2. And the length of y, well, the length of y isn't very, the length of y, remember, it's the square root of 1 times 1 plus 0 times 0. That's just 1. Let's put this together. So the cosine of theta is equal to the dot product, that's 1, over the length of x times the length of y. Well, that's just 2 times 1, that's 2. And I don't know if you've ever seen this double arrow. In math, it's very handy to write. It says, or it's read, this implies, or it follows. Or sometimes even just then. So if we have the cosine of theta as a half, it implies that theta is pi over 3 or 60 degrees. Now, there's one more piece here. Let's take a look at just one of these components. What is u times 1 over the length of u? It's called the unit vector. And we write it this way. We use a capital U, or in this case, we're going to use a capital X. No, let me do all. So in general, we'd say this. We'd say that U divided by the length, its length, it's the unit vector, meaning it's a vector that's 1 unit long. And if we take V and divide it by its length, then that's the unit vector for V. And our author uses a capital letter to denote unit vectors. So the unit vector for U is capital U. The unit vector of V is written as capital V. Well, what about X? What if we find the unit vector for X? Well, that is the length, 1 over 2, times the vector, which is 1 square root of 3. But this is 1/2 and square root of 3 over 2. Now, wait a minute. 1/2 square root of 3 over 2. Well, if I take half of the 1.7, that's about right here. But I just told you that the vector would then only be 1 unit long. The vector y is 1 unit long. What do we have? We have the unit vectors that fall on, my scale's a little off, that fall right on the unit circle itself. And so that's what the unit vector does. It takes any vector, no matter how long or even short, and it puts it right there on the unit circle for us. And that's how you find the angle between two vectors and how you use it. Thanks for watching.